Hey everyone, this is Andrew. Welcome back to the channel. In this video, I'm going to be discussing a basic introduction to stereochemistry. Specifically, I'll be talking about chirality, enantiomers, and optical activity. So in our discussion of stereochemistry, I always find this picture to be very interesting. So if you take a look at this, we see that your left hand and right hand, they're not identical, rather they are mirror images. So these mirror images, specifically handedness, is important in organic and biological chemistry. Handedness specifically arises as a consequence of the tetrahedral stereochemistry of an sp3 hybridized carbon atom. This handedness is extremely important in medicine, in biochemistry, as many drugs and almost all the molecules in our bodies have something to do with stereochemistry, and their functions are based off of their stereochemical functions. Stereochemistry allows for the precise interaction of different enzymes and their substrates and other hundreds of thousands of chemical reactions that occur. So with this being said, what exactly causes this handedness? If we take a look at this picture, we see that we have three sp3 hybridized carbon atoms. However, the substituents that are bonded to that central carbon atom differ in each of these pictures. So the first example, we have a CH3 with an X. The X can stand for any other element. Usually it's a halogen. If we take a look in the mirror, both the CH3X and the CH2XY molecules are identical to their mirror images and are thus not handed. If you think of your left and right hand, if they're identical, they're not handed, meaning they're not mirror images. By contrast, the CHXYZ molecule, notice the carbon atom at the center of the molecule is bonded to four different substituents. So when you take a look or put a mirror next to this molecule, it's not identical to its mirror image. You can't superimpose this molecule on a model of its mirror image for the same reason that you cannot superimpose a left hand on top of a right hand. Your thumbs would be on opposite sides. They simply aren't the same. So molecules that have this handedness, or remember, they are not identical to their mirror image, is a kind of stereoisomer that we call an enantiomer. And remember that an enantiomer, like we saw with this molecule, results when a carbon or another atom is bonded to, usually carbon or nitrogen, is bonded to four different substituents. Remember electronic geometry and molecular geometry. If you have a tetrahedral sp3 hybridized carbon atom, that's a carbon atom with four electron domains, we'll have tetrahedral geometry. And if it's bonded to four different substituents, say A, B, C, D, that atom is a stereocenter, and the molecule as a whole would be called an enantiomer. So let's take a look at an example of an enantiomer. Lactic acid, or 2-hydroxypropanoic acid, exists as a pair of enantiomers because there are four different groups, an H and OH is CH3, and a carboxylic acid bonded to a central carbon atom. Its two enantiomers are plus lactic acid and minus lactic acid. We'll talk about the plus and minus in another video. The plus and minus refer to how the molecule bends plane polarized light. So what's important about this is that no matter how hard you try, you will never be able to superimpose a molecule of the plus lactic acid on the minus lactic acid. A molecule that is not identical to its mirror image is said to be chiral, and you cannot take a chiral molecule and its enantiomer and place one on the other so that all atoms coincide. This presents us with a good problem. How exactly can we predict whether a given molecule is chiral or not? Let's take a look at these examples. Say we have a coffee cup and a hand. A molecule that is not chiral has a plane of symmetry. As we see here, a plane of symmetry is a plane that will cut through the middle of the molecule or any object in such a way that one half of the molecule is a mirror image of the other half. So when we take a look at this, the coffee cup is exactly identical to its mirror image. Therefore, this would be achiral, or not chiral. In the hand, as we've already spoken about, you cannot superimpose a hand on top of one another. Therefore, if we cut a plane of symmetry down the middle of a hand, both sides, or one side is not the same as the other side. So this would be called chiral. We can do the same exact thing with a molecule of propanoic acid. The one on the left would be achiral because that is a plane of symmetry. If you look, the molecule is the exact same. The mirror image of the left side is the same as the right side. If you take a look at lactic acid, there is no plane of symmetry. One side of the molecule is always going to be different than the other side if you cut a plane down the middle of it. So we refer to carbon atoms that are bonded to 4 different substituents, and there's not a plane of symmetry. So a chiral molecule, that carbon atom, that central carbon atom, would be referred to as a stereocenter or a chirality center. Do remember that chirality is a property of the entire molecule. So let's take a look at this example. We have 5-bromodecane. How can we predict if this molecule is chiral or not? First, we'll get to the carbon atom, the 5th carbon atom in this case, that is bonded to different substituents. So we have a bromine, a hydrogen, and then on the right side we have a CH2, 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 CH3. So there's 4 carbon atoms on the right side. In this case, we'll just refer to this as the left and right side of the atom, or the molecule. Then we have 1, 2, 3, 4, 5 carbon atoms on the left side. So what we see here, we have a butyl group on the right and a pentyl group on the left. We have a bromine above and a hydrogen below. This molecule, this compound, would be chiral. And in this case, the chirality center would be at this 5th carbon atom. Let's look at part A of this next question. We have to identify which molecule is chiral. Both of them could be, or not. Identify the chirality center. So just by looking at this, pause the video and try to figure this out. If you haven't done so already, we'll walk through it. None of these carbon atoms could be a chirality center. They're bonded to the same things. We have H's and C's, so there's no way that these could be chirality centers. However, let's take a look at the next carbon atom right there. This carbon atom is bonded to a propyl group. It's bonded to a amine group. It's bonded to a hydrogen, which is implied. And it's bonded to the rest of the chain. So the CH2, the CH2, CH2, and the CH2. So it's bonded to one group right here, another group right here, a hydrogen out here, and the rest of the chain. So that middle carbon atom right here would be our chirality center. Fun fact, this molecule is actually called conine. It is the poison hemlock. Fun fact. Let's go to this next molecule. Example B. This is menthol, which is a flavoring agent. If you've caught on to the trend, this should be quite easy. We see a chirality center here, here, and here. Notice the pattern. These carbon atoms are bonded to 4 different substituents. This carbon atom is not. It's bonded to 2 hydrogens and 2 carbons. Same thing with here. Same thing with here. So we would say that menthol has 3 chirality centers. 1, 2, 3. The first one is bonded to a methyl and a hydrogen. The next one is bonded to an OH and a hydrogen. And the last one is bonded to a hydrogen and an isopropyl group. So briefly before we end the video, I want to touch on optical activity and where the meaning of chirality truly comes from. So if you look at this representation of a polarimeter, plain polarized light passes through a solution of optically active molecules, which rotate the plane of polarization. So not all organic substances exhibit this property. However, those that do are said to be optically active, and those molecules are chiral. So what comes from this is that some optically active molecules will rotate this plane polarized light to the left or counterclockwise, and they are said to be levorotatory, whereas others will rotate polarized light to the right or clockwise and are said to be dextrorotatory. And that's where those plus and minus signs come from, if you remember. So this plus lactic acid rotates the polarized light to the right, or dextrorotatory, and the minus lactic acid will rotate polarized light to the left, hence the minus sign, or levorotatory. Hope you enjoyed this video. If it was helpful, make sure to like, subscribe. We'll be making more content. Specifically, I'll be touching on diastereomers, absolute configuration, and other topics having to deal with chirality centers and stereochemistry. Thank you for watching. I'll see you in the next video.